Alright, so today I'm gonna be explaining this important paper with the title Node Representation Learning in Graph via Node-to-Neighbourhood Mutual Information Maximization. This paper in 2022 from Monash University. The key towards learning informative node representations in graph lies in how to gain contextual information from the neighborhood. So in this work, we present a simple yet effective self-supervised node representation learning strategy via directly maximizing the mutual information between the hidden representations of nodes and their neighborhoods, which can be theoretically justified by its link to graph smoothing. Following info, I have explained this info and CE in a different playlist. So following that, our framework is optimized via a surrogate contrastive loss, where the positive selection underpins the quality and efficiency of the representation learning. To this end, we propose a topology-aware positive sampling strategy, which samples positives from the neighborhood by considering the structural dependencies between nodes and thus enables positive selection upfront. In the extreme case, when only one positive is sampled, we fully avoid expensive neighborhood aggregation. So we focus on node classification tasks in graphs, where the key is to learn informative structure-aware node representations by gaining contextual information from the neighborhood. This motivates a massive proliferation of message passing in GNN. So self-supervised learning has shown proven success in computer vision, natural language processing. However, it is less sufficiently explored in graph modeling. So they propose a simple yet MLP-based self-supervised node representation with the idea of maximizing mutual information between nodes and surrounding neighborhood. We reveal our end-to-end mutual information maximization strategy essentially encourages graph smoothing by resorting to a quantifiable smoothness metric. So, in any GNN, we have aggregation and update, and of course, a downstream task like this cross-entropy loss. So we want to learn topology-aware node representation by maximizing mutual information between hidden representation of nodes and their neighborhood, which is partially motivated by knowledge distillation. We denote the probability density function of the node representation H sub I over the feature space as this P. So the PDF, the neighborhood representation with the mapping function S, and the joint PDF between node and neighborhood is this P. So we can now define mutual information between their nodes and their corresponding neighborhoods. So this operation encourages each node representation to distill the contextual information presented in neighborhood representation. However, mutual information is notoriously difficult to compute, particularly in continuous and high-dimensional space. Fortunately, scalable estimation enabling efficient computation of mutual information is made possible through mutual information neural estimation. Because I've explained it in a different video, is using mutual information in a higher dimensional space. So it's a neural version. So this is scalable. You can use it in practice, which converts mutual information into minimizing info and CE loss. So the surrogate info and CE loss, if you remember, is this one. So it estimates mutual information via node sampling. Now this sim here is the cosine similarity. and this one is exponential. So the positive pair is S sub I and H sub I. And we have, of course, negative part in the denominator. So this is the positive pair, this is negative pair. And so maximizing I can play a role of graph smoothing. So they use this metric of smoothness metric of reference 18, this one. Now the work of this reference further proposes the information gained from neighborhood representation via the scale divergence. So they proved in a theorem that mutual information is inversely proportional to the KL divergence between the node and neighborhood. So they talk about topology-aware positive sampling. So firstly, the whole neighborhood can include redundant or even noisy information. Secondly, the aggregation is computation expensive. So we propose TAP's strategy for self-supervised node representation learning. The basic idea is that we measure the topological dependencies between a node and its neighbors and sample positives of the nodes based on the rank dependency values. So for two neighboring nodes, V sub I and V sub j, we can define the following joint probabilities. So X sub I can take value of either N sub I or V minus N sub I, because it's contextual information complementary to the neighborhood. So graph structural dependence between neighboring nodes V sub I and V sub j can now be written like this. The graph structural dependency value above, it measures the topological similarity of two nodes. So for training, unlike most existing graph-based self-supervised learning framework that uses GNN as node and graph encoder, we simply use a very shallow MLP for the encoder because it is more efficient. And in our joint learning scheme, we apply info and CE loss and cross entropy loss. So info and cross entropy, we have the hyperparameter to trade off between these two terms. And this is the loss that is backpropagated and left for learning the parameters. So you see the illustration of two training pipelines. You can either use joint learning or unsupervised representation learning. Here, info and CE is completely separate, but you use MLP to freeze the parameters here. It's kind of transfer learning, but here is a joint learning. You want to do both of the downstream task and this info and CE loss jointly. And they did experiments on PubMed, Quora sites here, these popular data sets. For example, they compare graph convolution with their method. You see from 84%, we just improve 4%, 88%. Or from 78, we just become 79. And they compare the time cost comparison. Time cost is in milliseconds. For example, for Quora, it takes 1.68 milliseconds for graph convolution, but for their model, it takes much lower. It is worth mentioning, when only one positive is selected, our model can fully avoid neighborhood aggregation, but it still maintains promising node classification performance. So the future work will be extending the proposed self-supervised node representation learning and neighborhood sampling to heterogeneous graph data.